The topic of my presentation today is how electrical vehicle can add stability to the distribution grid. And to get started, I want to make a short introduction of Delta Electronics. We are founded in 1971 by Bruce Cheng in Taipei, Taiwan, and in the meantime, a global leader of power electronics, automation, and infrastructure solutions. Today, we are having a global footprint with sales, R&D, and production facilities all over the world, with more than 80,000 members in the Delta family, and we achieved a revenue of more than 9.6 billion in 2020. We are spending year by year 6 to 8% of the revenue to the R&D activities and are holding more than 10,000 patents now. Our company mission is smarter, greener, together, and we are fully committed to achieving the climate goals with our high-efficient power electronics, PV inverters, energy storage solutions, and EV charging stations. And EV chargers are exactly the products I want to talk today about, and how EV chargers can add stability to the electricity grid. And therefore, I want to give you a short introduction of the Germany's electricity grid, the original design and the situation as it is today. I'm starting with this schematic here. You see the electricity grid in Germany is split into two systems, the transmission system and the distribution system. On top, we have the 220, 380 kilovolt lines, where we have connected the big nuclear power and coal power stations to really transmit the energy all over the country. These energy lines, transmission lines, are connected to the distribution system, which is split in 3 voltage levels. We have the 110 kilovolt lines, where we also connect big power stations to, but also big facilities like big production facilities and so on. Then one layer deeper, we have the mid-voltage line with a voltage level of 1 to 50 kilovolt, typically 20 to 30 kilovolt. Here we connect also industrial power plants, municipal power plants too. And on the other side, we have production facilities, industrial and commercial facilities that are directly connected with their own transformer stations then to the mid-voltage level. Finally, the low voltage, 230, 400 volts, what we all know from our houses, apartments, and so on. So this is then distributed in the cities and the villages and so on. The design is that the power flows, of course, from the utilities to the loads and from the high voltage levels down to the low voltage levels. And the tasks of the operator, grid operators, is that they need to ensure the voltage, that the voltage is within the allowed voltage range, to balance the production and consumption, to also keep the grid frequency stable. This balancing of production and consumption is also done by planning activities like redispatch and so on. And finally, of course, to ensure the stability, availability, reliability of the electricity grid. So what happens today to reach the climate goals and stop the climate change is, of course, that we want to decarbonize the production of energy. So we reduce the capacity of the conventional power plants, like the nuclear power and coal power. And on the other hand, we start to build up more and more renewable powers due to or with the installation of distributed energy resources. So the centralized big utilities get more and more replaced by decentralized distributed energy resources. This is, of course, very much needed to stop the climate change, but we also need to see what are the challenges coming with this change. The challenges are that the typical power flow from top to down is now changed, and we have also energy pushed back from the lower voltage levels to the higher voltage levels. So we have now here a bidirectional power flow, and this changes, of course, the voltage situation and so on in the grid. Furthermore, the renewable powers are not so much predictable and plannable anymore. We have, of course, forecast of irradiance and wind speed, but you cannot just easily control the irradiance and wind speed. You cannot, if there is no wind, you cannot just create it like you can control a typical conventional power station. So what are the solutions? Of course, smart grids and digitalization. I put here the cloud on top because we would need some services here. But, and this is another very important aspect, we need to add a big amount of energy storages to the distribution grid. 90% of the renewable power plants are installed in the low and mid voltage grid. So we need to add the storages here to buffer the renewable energy if we have more renewables than consumption, and to support, on the other hand, of course, all the loads if the production of the renewables is going down due to no wind, no sun. And the question is, of course, with the rollout of EVs, can the batteries of the electrical vehicles take over the battery capacity of this normally stationary storages? The EVs are standing 23 hours a day, not driving. So we have the battery capacity there. We ramp up EVs massively in the market now. So why not to utilize the capacity here to support the grid? This is exactly what we have been looking at in a research project in collaboration with the Brandenburg University of Technology Cottbus-Senftenberg. The project is called Intellect BB, Intellect Electromobility in the Federal State of Brandenburg. And the objective of the project was to develop and roll out a grid-supportive and green EV charging infrastructure solution. The project duration was in the last 2 years, 2019 and 20. We installed EV chargers at the Brandenburg University of Technology Cottbus-Senftenberg, but also on the 2 partner universities in this project, the University of Potsdam and the Eberswalde University of Sustainable Development. Besides the EV chargers, we provided also our charging station operator back office as software as a service solution. And of course, we had to develop a software to ensure a green and grid supported EV charging. The chargers we installed in the project are the ultra-fast chargers. We installed 5 of them with a maximum power capacity of 150, respectively 100 kilowatt. Today, this charger is available with 200 kilowatt and in the coming future with much higher power. The chargers installed in the project have been equipped with CCS, CHAdeMO, and AC Type 2 charging standard. We mainly used the CHAdeMO charging standard because we also had Nissan cars in the project. Then the chargers communicate to the backend via OCPP 1.6. We also provided 3 vehicle-to-grid chargers to the University of Cottbus with a maximum charging power of 22 kilowatt and a maximum discharging power of 11 kilowatt, also using the CHAdeMO standard and communicating to the backend via OCPP 1.6. For both chargers, or for all the chargers in the project, we also provided the installation and commissioning services. Besides the rollout of the charging infrastructure, as I said, we also had to develop a software to control the charging, to ensure that the charging is grid supportive, but also coming from the renewable energies. The software, we call the software Smart Charging Service Provider, and it uses a different input information to calculate the smart charging profiles. The input we need is the demand for the next ride, the utilization of the electricity grid, the available renewable power, and of course, all the status informations of the EV chargers. So let's take a look to the different parts here. The first is the demand. We need to know the planned drives with the EVs of the project. So we developed a smartphone application. You can see it here on the left, which is used by all the project members to enter the planned trips with the EV fleet of the university. So you take here the smartphone application, select the car, put in the driving distance and the time to depart, and save then this information to the system. We also developed a web application to manage the members of the project who can drive the cars, to manage the fleet of the university, and also to see all the trips that are planned. Next information the smart charging service provider needs is the utilization of the electricity grid. So you can see here on top the map of the federal state of Brandenburg. And this federal state of Brandenburg is here split into several grid clusters. This is done by the operators of the distribution grid. I have marked here one grid cluster with the black outline, but there are several more. This is the next grid cluster, then here one above. All the areas with the black outlines are grid clusters. And these grid clusters are connected via the 110 kilovolt lines. So these are the red lines you see here on the map going all over this federal state. So these are then the high voltage lines that connect the different grid clusters to each other. All the electrical information of this grid cluster are stored in a database operated by the university. And we have in this database the information about the generated PV power, the generated wind power, the biomass, all other generation, and also the consumption that happens within the grid cluster. The information is coming from the different distribution network operators, which are Midnetz Strom, EDIS, Stromnetz Berlin, WEMAG, 50 Hertz transmission. And they are, as I said, sending this information day by day to the database of the university. One data set in this database is very important. It's a balance. And this balance here, I have shown it also here in this chart below for the several grid clusters. This balance is finally the consumption in the grid minus the production within this grid cluster. So this means if the balance in the grid cluster is positive, it means the grid cluster consumes more energy as it produces. And therefore, energy is flowing via the 110 kilovolt lines in this grid cluster. If the balance is negative, the grid cluster produces more energy as it consumes, and therefore the power is flowing through the 110 kilowatt lines to other grid clusters. So as I said before, most of the renewables are installed at the distribution grid, and we know that this power flow is then, if we are exporting energy, this is really coming from renewable power. And the target of the software is, of course, to reduce here the extreme values to smoothen this curve, that we do not have so much power flow then on the 110 kilowatt lines. The next data the smart charging service provider needs is the status of the EV chargers. So we know from each EV charger, is it available, is it charging, with which power is it charging? Here, for example, 70 kilowatt. How many energy is charged to the car? We also know the state of charge of the batteries, because all this data is sent from the EV chargers to our back office. So how are all these things brought together? You can see this here in the system architecture. The EV chargers here at the bottom of the drawing, the EV chargers are connected via OCPP 1.6 to the back office. We have some special vehicle-to-grid APIs for the V2G chargers because OCPP 1.6 is not covering vehicle-to-grid applications. Then the data goes up to the smart charging service provider. This is the software we developed to calculate the grid supportive and green smart charging profiles. On the left-hand side, you see the grid database that I already introduced and which is operated by the University of Cottbus with all the information of the grid clusters. And on the right side, the smartphone, which you need to plan your next trip, that the system knows the demand. Based on all this information, the smart charging service provider calculates the charging profile and sends this via the charging station operator back office down to the chargers. So how is this smart charging service provider calculating the profiles? So first of all, we said if you connect an EV to the charger and it has a very low SOC, state of charge, we start to charge the car, because the most important thing is, of course, to ensure a certain state of charge in the battery, that if the car is needed urgently, that it is also available. This increases also the user acceptance, of course. And then we defined really here a range that can be used for grid services. And then the smart charging service provider, of course, knows the balance of each grid cluster, and depending on if the energy export on the 110 kilowatt lines is high or low, we can charge and discharge the car really to support the grid cluster. And for very heavy energy import, for example, we can discharge with a higher power. And if the energy import or export is not so high, then we control the charging to be charging or discharging with a lower power. Finally, of course, we need to provide a certain target SOC calculated by the demand. So you have put in the driving distance for the next ride with the smartphone application, so the system knows how much to charge the car to ensure that finally you can use the car for this ride. On the next slide, you see the system in action. So you have here really a chart about the grid balance of one certain grid cluster. The balance is changing a lot from negative to positive. For the first, where we imported energy from other grid clusters, we started to charge the car. Then the balance changed to be positive. So we needed to import energy and then used the discharging function to support the grid. So which means also that at the beginning we stored renewable power to the battery, and now we are using renewable power to support the grid again by discharging. So this is the state of charge of the battery. So we are discharging the car and using the energy to support the grid. And this changes here, as I said, a couple of times. So you see every time when the balance is negative, we charged, and when the balance is positive, we discharged the car. This brings me already to the conclusion of my presentation today. To summarize everything, the decarbonization and decentralization of the electricity production demand adaptations on the original electricity grid design, digitalization and energy storage systems can add stability to the distribution network. EV batteries can take the role of the energy storage systems, but something that is very important and need, of course, to be defined in the future are business models for these activities. that you really utilize your car battery for grid services. Also needs to have a financial benefit, for example. And other questions like the warranty for the EV batteries and so on. These are all things to be clarified. Yeah, this is the end of the presentation. Thanks a lot for your attention.